Hello, everyone. My name is Tinna Reynisdóttir, and I will be presenting our work on developing a specialized mouse model to establish postnatal malleability in Wiedemann-Steiner syndrome. Wiedemann-Steiner syndrome is a rare Mendelian disorder of the epigenetic machinery caused by heterozygous de novo disease-causing variants in the KMT2A gene. This gene encodes the KMT2A protein, which is a histone methyltransferase that places mono D and trimethylation marks on lysine 4 of histone 3. This syndrome is characterized by intellectual disability, pre- and postnatal growth retardation, and distinctive facial features, which you can see in these patient images, and hypertrichosis, which is excessive growth of terminal hair, often notable around the elbows. So another Mendelian disorder of the epigenetic machinery that is often associated with intellectual disability is Kabuki syndrome 1. Kabuki syndrome 1 is caused by mutations in the KMT2D gene, but these proteins, KMT2A and KMT2D, are very similar in a lot of ways. You can see here in this figure, they're protein domains. So most notably, their set domain, which holds the enzymatic function of the protein. So it has been previously demonstrated that Kabuki syndrome shows postnatal rescue of the neurological phenotype. And since these two diseases have considerable overlap of protein structure and phenotypes, that begs the question of whether Wiedemann-Steiner syndrome is also a treatable cause of intellectual disability. So in collaboration with Jackson Laboratory, we have created a mouse line using CRISPR-Cas9. These KMT2A lock-stop-locks mice carry a heterozygous cassette insertion in intron 1 of the KMT2A gene. This cassette is a stop codon or a loss of function variant that is surrounded by LOX-P sites on either side. So this insertion leads to early termination of the KMT2A protein and therefore causes Wiedemann-Steiner syndrome. So what's really interesting about this mouse model that it allows us to remove this cassette after birth. So we will do this by breeding our KMT2A lock-stop-locks mice to a Cree mouse line. So we get pups that have both these alleles. So what happens when we expose these mice to tamoxifen is that it triggers the release of Cree into the nucleus, which then cuts out the cassette at the LOX-P sites and causes the cassette to be deleted. By doing this, we will be able to test whether postnatal administration of tamoxifen can rescue KMT2A protein levels or any other phenotypical outcome measures. So we have created two independent mouse lines to be able to demonstrate that any results do not relate to CRISPR offsite targets, and this mouse model is homozygous lethal. Additionally, these mice have demonstrated decreased Mendelian ratios of the lock-stop-locks allele, indicating its functionality. You can see in these graphs here that these are results from genotyping ratios from breedings at the Jackson Laboratory. So for both mouse line 1 and mouse line 2, you can see higher percentages of wild type compared to the mutants. These mice arrived to us in March of 2021 and are currently in breeding. All pairs have had pups ranging from 3 to 8 pups per litter, so indicating that all of our males are fertile. And if this research project is successful, it will lead to a new fully characterized Wiedemann-Steiner syndrome mouse model for the international research community, as well as demonstrating robustly that there is postnatal malleability in Wiedemann-Steiner syndrome. Thank you all for listening.